Good afternoon, everybody. Good morning. I'm happy to be here. So I will talk about some machine learning paradigms which could be used for thermal power plants. So I will like to confess up front that I don't know much about the operation of thermal power plant. Rather, I don't know. But, I know a little bit about AI and machine learning. So I will talk about some potential, this thing. So before I start, I'd like to just know a little bit about your background. How many of you have a background of basic machine learning or artificial intelligence? If you could raise your hand. Okay, not everybody. And how many of you have some background on thermal power plants? Everybody. So good. We have complementary this thing. But, this will be a very basic talk. So all of us know, I'll keep this brief, that AI is a system for building intelligent agents. And today we see that AI is used in every sphere of activity because we want to augment what we are capable of doing to increase our efficiency and to be able to do things more efficiently than we can do. And because of this, AI has been ubiquitous in every field. And especially today we will talk about machine learning, which is the ability to learn from data. So typical process is that you have some data from which you learn and you get a model, and that model is used for inferencing and reasoning. Very simplistic view, but we'll just start with that. Now, in a power plant, again, please pardon me for my lack of knowledge about power plants sufficiently, but in general, in any manufacturing plant or power plant or chemical plant, where can machine learning or AI make a difference? We want higher quality output. Maybe that's not so much relevant, maybe, to a power plant, but definitely you want increased efficiency, you want to reduce cost, and you need to stick to the norms, whether it's of emission control, reduce wastage, and so on. So these are some of the places where AI can be used, and these are some examples which one can think of possibly. For example, the input. One has to look at what type of input to do to achieve efficient operation and cleaner combustion. Then how to do process control or optimize the process by deciding what set points for the process parameters to use so that the power plant can, or any plant can work efficiently. And last Mr. Ashish, Mr. Rajiv Das, and many people talked about different requirements that one has, and for that one has to optimize the process parameters to meet the demand requirements or many other norms. Then you need to do emission reduction. And of course, we had a talk on demand forecasting and management of energy, for which this sort of technology is used. And in the morning, many people have talked about predictive maintenance in order to detect when you should have some component for maintenance. And then industrial safety. So in an industrial environment, to see that there are no to inspect autonomously, especially in hard to access places, and to detect early that something is going to fail, or there's some accident might not happen, etc. Then autonomous inspection using image recognition. These are some of the few of those areas where machine learning and AI can be directly used in a thermal power plant, and there are many more things. This is just a model for possibly a data-driven plant operation overall. So there's a plant. The typical path is the yellow path. where you have the observation, experience of the operators and human decision making. On the other hand, if you have data-driven plant operation, you would have sensors which will collect the data, historically a lot of data under different conditions, and have an AI ML system which analyzes data and try to take a decision. Of course, that's the full automatic path. But what people try to do, and some speakers have mentioned about it, try to build a model of the plant or any component that you are going to model, what is called today very popularly as digital twin, so that based on the data, you can build a twin of the system on which you can try to see how it will work under different conditions and do different types of analysis. Now, if you talk about these different applications, they are fueled by data. And today, everywhere, in every industry, in every walk of life, even in our personal lives, everybody wants to collect data, and everybody wants to get benefit from data. And definitely in any plant, data is extremely useful to be able to use the data to build intelligent systems. And this has been facilitated by the rise of IoT and different types of sensors, and capture the different types of data, both structured data in terms of the different models, the different parameters, etc., and also unstructured data like images, video, text, etc., and utilize them for machine learning. Now, this is a very basic machine learning model flow. You have data, and then given a task at hand, you identify features which are relevant for that task. So extract the features or identify features from experts and build models on those features. Now, so the data, once you understand what is important about the data, so you can extract those features, or you can try to get derived features from those features. And the feature choice will initially may depend on the understanding of the experts in that domain. So they can be structured as well as unstructured and use relevant features. I may make some mistakes or a lot of mistakes in talking about power plants, but probably, according to some literature which I quickly studied, these could be in some tasks of a power plant, relevant to a power plant. You can think of these as features like coal flow rate, steam flow, steam temperature, main steam temperature, reheat steam temperature, steam inlet pressure, exhaust temperature, composition of exhaust, boiler temperature, and so on. So depending on the process that you are trying to model, you have to identify what features are relevant. And then you have to acquire those features. And as we saw that we can use IoTs and sensors to collect the data. Sometimes, this is one thing that, one of my colleagues, we have been talking about at some point, is that sometimes it may not be possible, it may be too costly to deploy very precise sensors which can collect, very good features, very good quality features. But one can also have a lot of low quality sensors which are cheaper, and even try to get whatever data one can have. As I said, you can image, text, any type of sensor, so that you have a lot of data and try to get value from that data. Some of the processes, for example, the operation of the plant, as we saw, is also a sequential process. So it's not just at a point you decide some input or some parameters and you get the output, that's the end of the story. It's a sequential process. And the data that one has to collect should be the time series data. And also in the operation of the plant, it's also a sequential process. And one has to look at machine learning paradigms which can continuously control the system. So this is the first part, is the feature extraction. Then, depending on the task, one has to choose a model. and the type of the model one chooses will depend on the nature of the task. So in the power plant, it's not just the task of having the plant operation. There are many different types of tasks, like inspection of something, visual, so many types of tasks. And depending on the nature of the task, one will choose some model. Some examples of basic machine learning models are like linear regression or decision tree, different types of graphical models, neural networks, deep neural networks, and so on. Now, with this basic background, I will talk about the basic machine learning paradigms in general. And possibly you can suggest, or you can think of what type of task relevant to a power plant they can be used for. So one basic type of machine learning paradigm is the supervised learning paradigm. In the basic case, what you have is you have different instances, and for each instance you have the input features, so the input parameters and the output, and you collect data about that. This is called labeled data. And then you build a model so that given the input, the model can predict the output. Okay, for example, suppose you are doing demand forecasting. So, the previous speaker talked about some of the parameters which dictate what is the demand, whether it is the time of the day or the season or, other things, weekday, etc., temperature, humidity, whatever is the parameters required. So you can collect the parameters, and you can have data about different time slots, and that historically, that was the demand in those days, and from that you can build a model. Then we have unsupervised learning, where you have a lot of data, but you do not have any labels. So this is called unsupervised learning, and there are different types of unsupervised learning. One common type of unsupervised learning is called clustering, and there are other types of unsupervised learning which try to form the model of the data. Then the third paradigm, which is also very useful, is the paradigm of reinforcement learning, which is especially useful when you have a continuous system. So you have you have an interaction, the system interacting with the environment continuously, and it's not just at a point you decide what is the output, but you have to take sequential action to decide the optimum policy. And we'll talk a little bit about these models now. So there's also semi-supervised learning, where you have some labeled data and a lot of unlabeled data. Now, so in supervised learning, which is the very basic form of machine learning, basic paradigm of machine learning, what you have is training data in forms of features, instances, where you have features and the output for every instance. And you have to find a function f, which given any xi can predict yi. Okay. So, I went through some of the few recent papers in this domain. So I'll just not talk about the full details about it, but this is one task that we came across. So, which is modeling the power production. So you want to know that given these inputs, how much power will be produced. So this is a very simple example, very standard example of machine learning, which can be applied to a power plant. So the features that they use is coal flow rate, main steam flow, main steam temperature, reheat steam temperature, etc. So these are some of the features which dictate what is the production of power. And in this particular work, they have used some machine learning methods, like one machine learning method is a support vector machine. And then one type of deep learning using an extreme learning machine, and a statistical methodology called response surface methodology. They have used this different machine learning methods, and they have applied on this task. And then they have seen that when they take data and they use a machine learning model. Machine learning model is a little complex. I'm not going into the details, but the basic machine learning model is this. And they are able to demonstrate that there are certain key performance indices relevant to this power production task, and they're able to show that with respect to these performance indices such as fuel flow rate, thermal efficiency, power plant heat rate, and the emission discharge, they are able to show that by building this model and using this model, they're able to improve on these tasks. So this is a demonstration that, so they had a particular task, which is efficient power generation with some net zero goal. And, they also look at not only the production, but also the regulations about these emissions, etc. And they're able to demonstrate that by using this machine learning model, they're able to get better efficiency. The second paradigm, so there are other examples of supervised learning. For example, there are a lot of people, tasks in manufacturing plants, I'm sure in power plants, there's a lot of case of using object recognition. So suppose, again, I do not know much about the plant, but there are different components. You want to understand whether a component is in the right state or not, or, if there are different states of a particular object. So people often use computer vision as a classification task to detect the state of an object or detect the presence of objects. So these are all supervised classification tasks. Then let's look at an example of unsupervised learning or clustering. So what is clustering? Clustering is one form of unsupervised learning. It's a form where one takes data which is not labeled and tries to find patterns in the data and find the main groups in the data. So group similar objects. And you can think of one application of clustering for anomaly detection. Suppose you have you have a lot of data of the normal operation of a plant. And then you apply clustering to find the different patterns. And you want to understand when there is some problem, right? And the main problem with understanding this is that the failure cases are very limited. So people who want to do, predictive maintenance, etc., the typical problem that they come across is that there are very few examples of failure cases, lot of examples of normal cases. This is where unsupervised learning is very useful, because if you take the normal cases and build a normal model, or in the case that there are different scenarios, you can find the major clusters or groups. Then if you find that your current data is not falling into any of these clusters, it means this is an anomalous data, or this is perhaps some problem is going to happen. So you can flag. So unsupervised methods are very useful for abnormality detection and to understand probably something is wrong. Probably this system is looking different or behaving differently than what normally does. And for that, this paradigm of unsupervised learning is very useful. So, as I said, anomaly detection using clustering, where you can look at the normal samples and characterize them in some way, either by clusters or by building a model. There are different unsupervised methods using normal machine learning or deep learning to build a model. Nowadays, there are lots of autoencoders and different, generative models, which can take the data and build models. And then you can find out if your data deviates from the model. So I found this paper, which talks about anomaly detection of power plant equipment using LSTM-based autoencoder neural networks. And what they have done is that they look at the time series data of the power plant operation, and based on this, they construct a normal model. And they use an LSTM autoencoder to try to find out whether the current data deviates from this normal model to find the anomaly. So this is a very important use case. The last type of paradigm I'll talk about today is the reinforcement learning paradigm. So reinforcement learning, you have the agent or your system which is interacting with the environment continuously. So at a particular time, the agent takes an action and then you get the output from that action. You get through your sensors and you take the next action. So it's not just one sort of parameters that you have to choose, but you have to continually interact with the environment. And in a plant, this is what happens. Okay. And so agent take action, which the system takes action which impacts the environment. And based on this, you perceive through your sensors how the environment is reacting. And based on your objectives, you also set up your cost function or reward function. So what is it that, whether it's a production or emission, so based on that, you set your rewards or penalties to decide how good they are. And the system works over a time. So this is the paradigm of reinforcement learning. And I saw a very nice paper which was published in AAAI, which is one of the premier AI conferences last year, which used reinforcement learning on the production of a thermal power plant deployed in some large power plants in China. And I'll talk a little bit about that. So in this work, what these people have done is that they have taken up the task of optimization of the combustion efficiency of a thermal power generating unit, which they call a TPGU. And they want to optimize this. And these are the steps that they have done. So they have collected the data. Now the data, the problem with data collection is that you only get data about what has happened. So the data typically may not contain all possible scenarios, right? And it is difficult. Typical reinforcement learning, there are ways where you can experiment with the system so that you can get more data of all types of scenarios and build a model. But that's not always possible because you don't want to deviate the process by which the power plant is working. So what they have done is that they have built a simulator which will give more data. So they have got some actual data. Using that data, they have built a simulator of the system. Sort of digital twin of the system, and use that to get more data. Now, the problem is that this simulator works on only the type of data that you have given. Now, if you use it on out of distribution data, you do not know how much you can trust the output. So, they have considered that in the later operation. But basic idea is that they have got some historical data called the offline data, and then they have used a simulator built on that data to collect more data. And using this data, they have combined data, they have trained a reinforcement learning model to decide how to control the power plant. So I found this total system very interesting. So I have limited understanding of the different components of the power plant, but if you permit, I'll talk a little bit about the portion that I understood. So what they say that the TPGU, because you people are experts, I'm not, but in this paper they say that their TPGU has these three major stages: the coal pulverizing stage, the burning stage, and the steam circulation stage. And in order to build the model, both for the simulator and for building the controls, they have considered all these different stages and what are the different control parameters and the requirements of each stage. And they have identified what are the important constraints and what are the important controlling parameters. For example, for the coal pulverizing stage, they say that the amount of coal should meet the demand load. Then the valves of the cold and hot air blowers have to be adjusted to ensure suitable primary air temperature. These are some constraints. For the burning stage, they say that the valves at each of the injection location, the 20 to 48 locations, they need to be controlled precisely. And then there are safety and regulatory issues that need to be guaranteed. so that you have this pollutant norms, negative internal pressure, they have to be maintained. For the steam circulation stage, they said that the steam generated needs to satisfy multiple temperature and pressure requirements, which are controlled by the valves, etc. So whatever it is, so in a typical plant, there are a lot of different components, and they have their behavior, and they have what are need to be done. This is only partly part of what is reported in the paper. There are several other things. So there are many such number of control parameters. So what they have said is that in their work, they look at about 70 to 100 major continuous control variables and the chemical properties of the coal, that is the input materials. Now I'll take a digression. I'll talk about the very basics of reinforcement learning. In reinforcement learning, so then the basic form, we assume that the underlying model of the system is a Markov decision process, where at a particular point there is a state, and when you take an action, the system changes state in a manner which is stochastic, but which is Markovian. That is, the next state is not fixed, is not necessarily fixed, not deterministic. It may be stochastic, but it only depends on the current state and the action. So, and you receive a reward. For example, if there's more production, there's more reward. If there is more pollutants produced, then there is penalty. So reward and penalty are there. Policy is how the system is behaving. When you're controlling the system, what are your control actions? So you are trying to understand that each state, what is the action that you should take? That is the policy. That is what you want to learn. And your objective is given by a value function. Value function combines the reward and penalty that you get into a function which you want to optimize. And the policy that you have to decide is that action at every state so that this value function is optimized. So for this, the underlying model is taken to be a Markov decision process, which has states, actions, rewards, transitions, and value function. And the way you construct the value function, there are different ways. One of the most popular type of value function is the discounted sum. So R0, R1, R2 are the rewards / penalties at different time steps. And they are added by taking a discounted sum. So the reward now is not discounted. The reward next time step is discounted by gamma, next time step by gamma square, where gamma is a number between 0 and 1. So this is your utility function which you want to maximize. And the value of a policy at a state is the expected utility. Why expected? Because the system is stochastic. You don't get exactly the same output when you give the same input, but it behaves in a stochastic manner. So you want to do the expected utility. Now, there are various reinforcement learning algorithms. One of the offline, what they use is offline reinforcement learning. What is that? They first, based on the data that they have, offline data, fixed data, you learn a model. Basically, the model is an MDP. You learn the parameters of the MDP. What are the parameters? You know the states, you know the actions. You have to learn the transition function. That in this state, if you take this action, what is the probability distribution of the next state? You also want to understand the rewards. In this state, this action will give you this reward. So, based on the data, you learn the MDP. And then once you have the Markov decision process, there are some standard algorithms using dynamic programming where you can find the optimum policy of an MDP so that at every state you can maximize the value function. And for that there are two standard algorithms like policy iteration, value iteration, etc. And we'll talk about this later. Now, for an TPGU that we talked about, the state that they have taken is the chemical property of the coal and sensor data, including temperature, pressure, wind, water volume, etc. So this is the state they have taken. The actions are the key control variables that impact the combustion process. We talked about that. They have taken 70 to 100 different control variables. And the reward function is a weighted combination of combustion efficiency and reduction in NOx emission. And the cost function, they have safety constraints, etc., which are the regulatory norms. Now, based on this, as I have told, they have first, in order to augment the data, they have built a simulator. Even to build this simulator, they have used a data-driven machine learning approach. Okay? Again, I'm not going into the details, but they do an approximated dynamic model to generate future states. And in order to build the simulator, they do not build one monolithic simulator. Rather, for these three different stages, they have used different machine learning models based on the parameters, etc., and using an RNN, LSTM, fully connected network, different types of neural network. They have built the simulator, which is faithful to the data that they already have. But as I said, they may not guaranteed to work well on the out of distribution data. Now, once they have built a simulator, so that's why this is called an imperfect simulator. And they have also, to build a reinforcement learning system, they have a cost critic, because they have to abide by different regulatory norms. So the cost critic to enforce the safety constraints, etc. And also they take into account the risk of the simulator, because when the simulator works on out of distribution data, you cannot trust it fully. So they quantify, they also model the risk. And based on that, they have built a reinforcement learning model which can decide the control actions of all the 70 to 100 control variables. And they demonstrate in this paper that they have used this control on 4 different large thermal power plants in China, and they have quantified the improvements that they have got. In most cases, they have got a reasonable amount of, good amount of improvements by using this process. So this shows that, in the power plant, they have been demonstrated that the use of machine learning has a lot of, people have used it and they have found a lot of benefits, and there are a lot of potential of using further systems. With this, I will stop. Thank you.